Sure. Okay. So last time when we left off, we had started working on addition to alkenes. And the last big idea that we covered was that when you are doing an addition to an asymmetric alkene, there's this rule called Markovnikov's rule, which tells us that the electrophile is going to go to the least substituted carbon of the alkene, and you end up with the more substituted product. And we discussed why this is, which is that when you use the pi electrons to attack the electrophile, you create a carbocation. And the more stable carbocation is more likely to form, and therefore the one that's going to lead to the product. So in order to get to the more stable carbocation, you have to put your electrophile on the least substituted carbon so that the carbocation ends up forming on the more substituted carbon. So we also did this example before we finished up where we did a reaction with hydroiodic acid, and we saw that the pi bond attacked the proton and we formed the carbocation on the tertiary carbon, and then the iodide came and attacked the carbocation, giving us a tertiary alkyl halide as our product. We then also did an addition with a dihalide molecule where we had an atom of iodine and an atom of chloride. And we talked about how this molecule is polar and that iodide is the more positive atom. So that's going to be the electrophile in this reaction. So the pi bond attacked the iodine. We broke the bond to chlorine. We created the more substituted carbocation, and then chlorine came in and attacked, giving us this final product. So this type of reaction is called a regioselective reaction. Regioselective reaction just means a reaction that can possibly make two or more constitutional isomers, but it preferentially or exclusively makes only one. So Markovnikov addition is a perfect example of this because just looking at the alkene, you could see potentially two possible products, maybe more if you think about carbocation rearrangements, but it's going to favor creating the more substituted product. So then the next question is, what if we need to synthesize the less substituted alkyl halide? And this gives us anti-Markovnikov addition. So Markovnikov gives us the most substituted, anti-Markovnikov gives us the opposite, it gives us the least substituted. So if you were to take an alkene and react it with hydrobromic acid, you're going to end up with the most substituted alkyl bromide. But if you do the same reaction and add in a peroxide, so it can be a dialkyl peroxide or it could be like hydrogen peroxide, but usually you see an alkyl-based peroxide. You'll end up with the anti-Markovnikov addition where the bromine ends up on the least substituted carbon. This process actually happens through a radical reaction, which is chapter 10 chemistry. So for now, we're not going to worry about how this happens. We're just going to remember that this does happen and that this is a way that you can create this product. A really common type of question for this chapter is I give you this and I give you this. You have to give me this. So you need to know your reagents and what they do. Are there any questions so far? Okay. So in the presence of a peroxide, anti-Markovnikov addition occurs. We only do this with hydrobromic acid. Whoops, that was some bad animation again. So the stereochemistry of addition to an alkene it's not very complex. It's the same situation as when you had an SN1 reaction. If you go through a carbocation intermediate, you are going to lose any stereochemistry that you may have started off with, and you're going to end up with a racemic mixture. So in this case, not only do you have a carbocation intermediate, but we're starting off with an alkene, which is also trigonal planar. So we go from a trigonal planar alkene to a trigonal planar carbocation, and then we add something else in, and we end up with a racemic mixture because we did not have any stereochemistry to dictate otherwise. So the carbocation intermediate here, when you go to add in the halogen, it can attack from what we'll call the top in this situation, which would give you this product. It's going to push the methyl group and the hydrogen down. Or the halogen could attack from the bottom, which would give you the enantiomer. Are there any questions about this so far? Okay. Okay, so our next reaction is acid catalyzed hydration. So this is the exact opposite of dehydration. So your alkene is going to start off, and it's a Markov-Nikov addition also. So we're gonna look at the mechanism here. I'm pretty sure I didn't draw it out. Yeah. Okay. So in this mechanism, you have water and acid as your reagents. It doesn't really matter what the identity of the acid is. Usually it's given to you. Common conditions for acid catalyzed hydration include like 0.1 molar sulfuric acid. This tells you that you have a lot of water and a little bit of acid. The first step here is going to be to protonate the alkene by stealing a proton from the hydronium that would exist in that solution. A lot of students often forget that this is the first step, but anytime that you're looking at a reaction, if it's an acid, your first step is to protonate something. That's going to be true for the rest of organic chemistry. If you are in acidic conditions, your first step is always to protonate something. So if I have carbon A and carbon B, which carbon is the hydrogen going to go on?
Would it go on A?
So if we put the hydrogen on A, we'll end up with a carbocation on B. Is that the best carbocation?
No. Okay, you're right. B.
Yes. So if you have a hard time remembering like where you should put the hydrogen, ask yourself where you want the carbocation. We know that we want the more substituted carbocation, so the hydrogen has to go on the other carbon. Okay, and then we also have water. What's going to happen next?
The oxygen is gonna attack the. Honestly, never mind. I don't know.
No, I think you're going in the right direction. All right, the hydrogen, or sorry, the oxygen is going to attack the carbocation. So you have something partially negative. It's going to be interested in the positive charge. Okay, and I'm going to stop drawing this hydrogen because it becomes assumed it's part of this methyl group. So we do not need to keep drawing it. Okay, we're almost to our product, right? We want to get to here. What do we need to do to get to that product? What is the difference between these two molecules?
Something comes along and takes an H from the H2O.
Right. So we have a lot of water in this reaction. It's going to come along and deprotonate it. Okay, any questions?
This was just an example of Markov-Nikov, right? Not anti.
Right, this is Markov-Nikov addition. So far we've looked at Markovnikov addition of a halogen acid, and then we saw the anti-Markovnikov addition. Now we just did Markovnikov hydration, and now we're going to look at the other varieties of hydration. So before we get to anti-Markovnikov, we have a different type of Markovnikov. So the mechanism summary of acid catalyzed hydration is 1, protonate the alkene. 2, form the most stable carbocation, and you may need to rearrange. 3, water attacks the carbocation. And then 4, you deprotonate to form the alcohol. So that is your mechanism every single time for an acid catalyzed hydration. Okay, so I have a practice problem for you guys. I'm gonna go ahead and put you guys into breakout rooms.
Sorry, could you go back to that list real quick?
Oh, sure.
There we are, thank you.
Okay, I'm gonna put you guys in breakout rooms. This right here means that it's a catalytic amount of sulfuric acid. So this is essentially a solution of very little sulfuric acid in methanol. There is going to be a carbocation rearrangement of some sort, so keep that in mind. Those are my hints for this problem. Okay, so go to the room when you have the reaction written down. Okay, so what is our first step?
Does the double bond attack the hydrogens on H2SO4s?
Right, so there is a proton in here. You don't have to draw H2SO4 if you don't want to. It's just going to pick up a proton. Whoops. What is happening? I'm not trying to leave. That's rude. Okay, sorry. Okay, we have carbon A and carbon B. Where is the proton going to go?
Carbon B.
Yes. So we have a carbocation on carbon A. Okay, so remember, anytime we make a carbocation, we need to ask, is this the best one we can make? Is this the best carbocation we can make?
No.
No. What are our options for rearrangement?
You could do the ring, what was it, expansion.
Right. So here you end up with kind of a debate, like, do I want to do a hydride shift and end up with a tertiary carbocation, or is this cyclobutane going to bust open? If you have a cyclobutane busted open, it is not happy where it is. So let's go ahead and expand the ring. This is going to give us a 5-membered ring. So again, we can number everything if it helps us. So we should have a methyl group coming off of carbon number 1. And where is our carbocation going to be?
On carbon 1.
Well, so it started off on carbon 1 and we moved some electrons there. Which carbon is losing electrons?
2.
Yes. So carbon 2 is losing electrons. I'm actually going to number in the opposite direction, just so we can continue the mechanism on this side. Okay, so now we have our carbocation, and we haven't really talked about this, but you can only really do one carbocation rearrangement. Each one has a pretty high energy cost, so we're not going to do a hydride shift and move it over into the tertiary carbon. That's just too high energy. What's going to happen next?
Would that become a double bond on there?
How?
The methyl group moves?
No. Well, so what's the other thing that we have in this reaction?
Yeah, you gotta have water attack the carbocation. So basically, yeah, the water attacks the number 2 carbon.
Okay, is there water in the reaction?
Would you use a CH3OH?
Yes, so basically we subbed in methanol for water. Okay, and then what happens next? So remember, this is not different from the reaction with water. Like we just put in an alkyl group in the place of a hydrogen, right? So what's going to happen next?
Would you take away one of the hydrogen on there to give the electrons to the oxygen?
Right. We don't want to have this positively charged hydrogen, oxygen. So we're going to deprotonate it. Whoa, that was weird. Sorry. Okay. So we end up with this ether as our main product. And then Madison said something earlier about creating a double bond. And honestly, that's not wrong. One of your side products for this reaction, if this reaction were heated, there's a very good chance that the methanol could pull off this hydrogen and create a double bond. But it would require some heat to be added.
Because there's not enough energy, like you said earlier.
Right. Yeah, trying to pull off a proton in acidic conditions is pretty difficult. But it would essentially be the opposite of a dehydration, or sorry, it would be the opposite reaction. It would be a dehydration. So you would have to have heat to do it and concentrated sulfuric acid. So that wasn't a wrong thought. It's just the conditions aren't quite right for that. Okay, so here's our major product. Okay, are there any questions about this one? Okay. Okay, so next we have another type of hydration. And as you guys now have seen, you can sub in alcohols in the place of water, and instead of getting a hydration, you'll get an ether. Same thing. So oxymercuration demercuration is a process that gives you a Markovnikov hydration without the possibility of carbocation rearrangement because it does not go through a carbocation. So if you take a simple alkene like this, where the alkene is on the first carbon, you end up with the same result. But if you use a structure where a rearrangement would be possible, what you end up getting is Markovnikov addition without any sort of rearrangement. So if we just did this in H3O+, we would end up doing a ring expansion, and we would end up with cyclohexanol as our product. But if we did this with oxymercuration demercuration, we would just end up putting our hydrogen here. We'd have a carbocation here. We would end up attaching our alcohol right there. So it's still Markovnikov. We're not getting the least substituted product, but there is no rearrangement. Do we see the difference between these two? Actually, I meant to change this example. I got this from the textbook, but there's an issue with this rearrangement. I'll go back and fix that. I should have fixed it previously, but I wasn't thinking. I was just copying my original notes. So this is a bad example right here because that compound would not be created, but this idea is still correct. So our other conditions are hydroboration, oxidation. This is our anti-Markovnikov option. So if we were to take this alkene that we started off with as our example previously and do this with these conditions, we would end up with the anti-Markovnikov product. So real fast, I realized I didn't go over the conditions of the previous example. So this is a mercury diacetate salt. And then you have water and THF complex. THF is a cyclic ether. And it's a solvent. And then in the second part of the reaction, you would add in sodium borohydride, which is a source of hydride, and sodium hydroxide. So hydride is not particularly stable on its own. So this is a way to add it in a more stable version. So the reason I wanted to point this out is that the THF gets used a couple times. Also, we haven't seen too many reactions where it was step 1 and step 2. When you see that, that is important. So if I asked you to provide these reagents, you would also need to have it written out as step 1, step 2. If you combined all these things together without separating them, it would not actually work. So in our next one, we have a borane THF complex. So it's the same THF cyclic ether, and it's actually complexed with the borane BH3. And then in the second step, you add in hydrogen peroxide and sodium hydroxide. So again, this is a step 1, step 2 reaction. If you put them together, it won't work. And the mechanism, I'm not going to make you guys learn the actual mechanism of how this stuff forms, but understanding this intermediate here can help you see why it's anti-Markovnikov. So the borane actually gets added in the anti-Markovnikov method. So the boron atom gets added to the end carbon of the alkene. And then it adds 3 times actually, which is kind of bizarre. So you end up with 3 equivalents of your alkene attached to the same boron atom. And then you add in an excess of hydrogen peroxide and sodium hydroxide, and it essentially ends up displacing the boron. That's not exactly what happens, but that's the essence of the thing. And that's how you end up with the anti-Markovnikov product. The other important thing to note about this is that while other addition reactions to alkenes are typically not stereospecific, the hydroboration oxidation, if you do this with a cyclic compound, it's important to know that this reaction actually is stereospecific. So it's not really going to matter if the alkene is linear, but if it's cyclic, it's important to note that the hydrogen and the alcohol get added to the same face of the ring. So your product, excuse me, is always going to end up with the oxygen and the hydrogen that you added on the same face. So typically if there's a substituent on the alkene, it's going to end up trans to the alcohol. So if you were to draw this alcohol flat, the alcohol would be down and the methyl group would be up. So the alcohol will end up on the opposite face of anything that was on the alkene. And also you get the anti-Markovnikov product.
Can you repeat that last part one more time? You said what when you have what, it makes them on the same side?
So the hydroboration oxidation reaction puts the hydrogen and oxygen on the same face of the ring. So if you have any substituents on the alkene, they will end up on the opposite side from the alcohol. So I don't know if I said syn addition, but syn addition is the phrase that's used to describe this when it's added to the same face of an alkene. Sorry, today might actually be the day that I lose my voice in class. So I created a chart of all these hydration methods because that's kind of a lot. So you have your acid catalyzed hydration. This is your generic acid and water. It's Markovnikov. There's no control of the stereochemistry. If a rearrangement is possible, it will happen. For oxymercuration, demercuration, it's also Markovnikov. There is no control of the stereochemistry. And if a rearrangement would be possible, it's not going to happen. For hydroboration oxidation, it's anti-Markovnikov. It's stereospecific. You get the syn addition, and there is no possibility of rearrangement. Okay, our next reaction is the halogenation of alkenes. Oh, you know what? I have a top hat question. Okay, pretty sure this is the question I want to ask. I need to change the titles to things that actually tell me what the question's about. Okay, so we're going to start a presentation. We'll go ahead and take attendance. Okay, I'm going to just minimize this so we can keep going. See, I was talking with one of the top hat reps and they're like, why aren't you using it more often? And I was like, it's slow. And this is a good example of this. I think once I get back on campus, next semester, I'll teach my classes from campus, even though they're online. The internet's faster. Okay, so it says, consider the following hydrohalogenation reaction below. What relationship did the two possible products have with each other? And then I'm going to shrink this image. So even though Top Hat is slow and it can be frustrating, I wanted to go ahead and do some of these questions since you guys are taking a quiz tomorrow. So this is kind of your pre-quiz practice. I'm also opening up a bunch more homework assignments.
Have you uploaded that flow chart that you showed us yesterday?
No, I did not. I will do that after class. Sorry. Thank you for the reminder.
Thank you.
Sorry, I'm still just trying to keep up with you guys. We keep moving so much faster than I think we will, and I never have enough material. Yesterday, if we'd gone on for 5 more minutes, we would have run out. So I guess I do have enough, just barely. Okay. There's one person who hasn't answered. I'm going to give you another 5 seconds. Okay, great. Well, maybe this is good. It's going to slow you guys down. I pushed the close button about 10 seconds ago and it's still saying stop answering. Cool, cool. I know it looks like I'm just like hovering over the button, but I swear I pushed it. Okay. Oh no. Guys, come on. They are, you can see them. They're not, oh no, you're right. I'm sorry. I forgot about this carbon. Wow. Okay. You guys are great. Normally the answer would be enantiomers, but we have this third group over here that I completely forgot about, but you guys did not. Okay, let's see what the next question is. So it says label the products of the following reaction as major or minor. It's telling me I cannot start the question. Come on. Okay.
Showing up for us.
Okay, that's good. If it closes, let me know. I'm a little worried that I may have clicked twice. I did.
Yeah, it's telling me submissions closed. I
Sorry,
haven't.
let me open again. Sorry, I think it's because I clicked twice on the forward button. Is it open?
Yeah, it's open now.
Okay. It's not on my screen, but that's as long as it says it on yours.
Isn't Top Hat fun?
It is, yeah. I think it would be much better if we weren't also on Zoom. Plus, I hear talking coming from the office, so I think my husband is on Zoom as well, which is not helping.
I don't know. It beats clicker question.
I'm sorry, you cut out. I think maybe you muted yourself in the middle of your response.
Oh, I was just saying it beats clicker questions.
Oh, I agree. Yeah. This is much better than trying to write a question that can be answered via clicker. Okay, so I am going to close it on purpose in about 10 seconds. Sorry, I see I have a question via chat, but I tried to open it and now I think Zoom is kind of frozen for me. So I'm going to close the question. Okay. Okay, so did only 17 people answer? Or no, this is the most popular match, I see. Okay. So I think we're good. Product A is our major product. The hydrogen is going to go to the less substituted carbon, even if that substitution is a chlorine. And then the other chlorine will end up there because this carbocation, putting the carbocation on this carbon is going to be more stabilized by the electron density of the chlorine. So the hydrogen goes here, your carbocation goes here. This is going to be your major product. This will be your minor. Okay. I had planned on doing 6 questions. I'm thinking we're only going to do 3. It's taking too long. Okay, so on your screen, you can see the entire question in one image, right? It says match the following reactions with their predicted products. I believe the question is open. The second reaction is not something we've necessarily done. but you can, I think you can figure it out. Think about what sulfuric acid would do, and then think about what sodium bromide would do. I'm going to put a 60-second timer on since this is a more challenging question. About 20 seconds left. Sorry, I couldn't announce our time because my computer froze. So on my end, it says stopped. I hope it says stopped on yours. Okay, so let's look at these
Yes, it does.
reactions. Thanks. Let's look at these reactions before we look at our responses. So in the first question, it says dilute sulfuric acid is our conditions. What does dilute sulfuric acid mean?
There's water.
Right. So what type of reaction are we doing if we have an alkene and aqueous acid?
Wait, no. It's not dehydration, isn't it?
No, it's the opposite, right? So it'd be
It's the hydration.
right. Okay, so we should be looking for a product with an alcohol in it. So that should narrow you down to B or E. And then what are the rules of an acid catalyzed hydration? Do we get the Markovnikov or the anti-Markovnikov product?
Markovnikov?
Right, so between B and E, which one is the Markovnikov product?
B.
B, right. Okay, our next problem, we have concentrated sulfuric acid, which means there's no water present, and we have sodium bromide. So what is the role of the sulfuric acid here?
To take away the double bond.
Right, it's to protonate the double bond, right? So this is essentially equivalent to having hydrobromic acid. So we are looking to protonate our alkene to create a carbocation, and then you have bromide floating around. So which two answers could we narrow it down to just using that information?
C or D?
C or D. And is this going to be a Markovnikov or anti-Markovnikov process?
Anti?
No, it's just going to be Markovnikov. There's no peroxide present, so it's not going to be anti. So is it going to be C or D?
C?
Right. And then number 3, we have a tertiary alcohol in concentrated sulfuric acid and heat. What does the heat tell us is likely happening? What type of reaction is favored by heat?
Elimination.
Right. So we know that we are forming what functional group?
Alkene?
Right. So at the very least, if you know that heat favors a double bond, that limits you to option A, right? So this is a dehydration. Okay, let's see how we did. I guess our answer should be B, C, A. Excuse me. Oh, I see the conditions for number 2 kind of threw us off. These letters are very confusing, but yes, B, C, A are our products. Well, only 4% of us got all 3 correct. So I think that's a person, maybe 2. Oh, wait, no, we're not doing any more of this. It's taking way too long. Okay. So we're gonna go back to PowerPoint. I'm gonna try to end the top hat presentation. Okay. I believe I've asked it to end the presentation, so we'll see if that happens. Okay, you guys are seeing the PowerPoint again?
Yes.
Yeah, great. Okay, so halogenation of alkenes. Halogenation is where you react with a halogen molecule. Remember that halogens are diatomic elements, so they exist as diatomic molecules. So if you react an alkene with Br2, Cl2, I2, you are going to get, okay, I see some of you guys were having top hat issues. Just send me an email later and I'll worry about it then. You're going to end up adding a halogen atom to each carbon of the alkene. This addition is also going to be in a trans format, which is why I drew it the way I did. Obviously on ethene, going to ethane, there's no stereochemistry here, so it doesn't really matter, but when you get to cyclic ones, it will. So for example, if we have cyclohexene and we react with molecular bromine, we're going to end up, excuse me, with trans addition of the bromine, and we will also end up with the enantiomer, which I don't see drawn on here. So you'll end up with 2 products. This is known as an anti-addition. So previously we had syn addition, where both pieces of the reagent were added to the same face. This is an anti-addition. They're going to be added to the opposite faces. So we're going to go through the mechanism. It's not too challenging, and it does, I'm not trying to escape. I understand why it thinks that, though. I accidentally pushed the escape button while trying to detach my keyboard. Okay, so in this mechanism, the pi electrons of the alkene attack one of the bromines, which in turn attacks the other carbon. and this causes the bond between the two bromines to break, and a cyclic structure featuring a single bromine atom to form. This structure is called a bromonium ion because there's a positive charge on the bromine, and you will often hear the term bridging bromonium ion because it's bridging the two carbons together. Now that you have this, the bromonium ion is going to be a cis structure. So the entire three-membered ring that you've formed is going to be on one face of the cyclohexane, which means when the other bromide ion comes along, it has to do a backside attack. This is essentially just an SN2 reaction on the bromonium ion. So we have the bromonium up on one face of the cyclohexane. The bromide can come and attack this carbon from behind, or it can attack this one from behind. Depending on which one it attacks, you'll get a different product. If you use the bottom one, the bromine on the bottom will be pointing down. If it attacks from the top, you'll end up with this. And since there is an equal possibility that either one of those things will happen, you will end up with a pair of enantiomers. But of course, as we saw in the other question that I asked you guys, if there were another something on here, they would not be enantiomers, they would be diastereomers. But this portion of the molecule is going to be enantiomeric.
So the one on the left is if it got attacked from the top?
The one on the left is if it were attacked from the bottom. So when this bond is broken, the bromine ends up attached to that top carbon, and the one that did the attacking is on the bottom carbon. So it's going to be from underneath. Does this make sense? Do we understand why the stereochemistry happens? Okay. Because I know it's hard to remember which ones have what type of stereochemistry. So I think if you know how it happens, that can help you remember. So this is considered a stereospecific reaction. So regioselective, we looked at earlier, means like it prefers a certain connectivity of atoms. Stereospecific means it prefers a specific arrangement in space. So when a particular stereoisomer of a starting material yields a specific stereoisomer of a product, we call that a stereospecific reaction. So for example, if we were to take a transalkene and react it with bromine, we end up adding the bromine to opposite faces, and you end up with a product that looks like this. These are actually kind of difficult to picture. Let me see if I can demonstrate. So remember that the alkene is flat, right? So when the bromonium ion forms, it forms, say the alkene is in the plane of my arm, it forms on one side. Now that's only thinking about these two center carbons. You also have these two methyl groups. So if we have the alkene here, we have one methyl group, this is my TV remote, sorry, one methyl group coming towards you and one going away. So when the bromonium ion forms, it's out of the plane of these other two things. And then it comes and gets broken by the other bromine. This is going to force one methyl group up and one methyl group to be down. And so that's why we have this final structure that we have. The methyl groups end up going in opposite directions. Now this should have an enantiomer, but if we rotate around our single bond, bring the bromines not only in the same plane, but pointing in the same direction, we'll find that this is actually a meso compound. So there is not an enantiomer. If you take a transalkene that is symmetrical and react with bromine, you end up with one product. And this is going to be 2R3S23-dibromobutane. Now, if you take the cis alkene, the methyls are pointing in the same direction. So in the product, the methyls will end up in the same direction. But remember, the bromines still have to be trans. So you end up with 2 enantiomers. You end up with one that is 2R, 3R, and 2S, 3S. Does this make sense? Now remember, if this alkene were not symmetrical, you would not have a meso product in this top reaction. You would end up with 2 enantiomers. Oops. So me asking you to draw out the specific product stereochemically from an alkene like this, I don't do that very often. Usually if I'm looking for a stereo-specific product, it's coming from a cyclic structure. So our next reaction is the formation of something called a halohydrin. This is a functional group that we haven't really done yet. So if you do a halogenation in the presence of water, the water actually ends up interfering. So the halohydrin is where you have a halogen on one carbon atom and an alcohol on a neighboring carbon atom. You will also end up with the vicinal dihalide as a product, and also an equivalent of halogen acid. So you end up with a mix of products. This is not really an ideal reaction, but it does happen. And the mechanism here is that you end up with your, whoops, got a positive charge. You end up with your bridging halogen ion, and then the water is going to attack, and you would have to deprotonate the water just like you did with the hydration mechanism. But you end up with alcohol on one carbon, halogen on the other. There is some regioselectivity with this reaction as well. So if you have an asymmetric alkene, when you form that bridging bromonium ion, the water is going to preferentially attack the more substituted carbon, which is a weird concept. That's not what we usually see with substitution type reactions. There is a reason. I don't think it's overly important to go over it. Essentially, this carbon has a little bit more carbocation character than this carbon does. And so the water is more attracted to it. But it's going to attack here, and you break open the ring just like you did in the other reactions. But you're going to end up with the alcohol on the more substituted carbon. Are there any questions about halohydrin formation? No? When I made this last night, Golden Girls was on, and so now I'm thinking about that episode. It's distracting. I'll try not to watch Golden Girls while working on notes again. So, okay, we have a couple more reactions to go through, and then we are probably going to finish this chapter early. I think it's only 11:06. I don't know. We'll see. So the next one is the hydrogenation of alkenes. Oh no, I just realized all the other chemistry that's in this chapter. Never mind. We're not finishing today. This is a long chapter. If you react an alkene with hydrogen gas in the presence of essentially any transition metal, but mostly platinum, palladium, or nickel, you're going to end up creating an alkane. So this is still just an addition across the double bond. We've added hydrogens to each of these carbons. So remember, in the original structure, there would be 1 hydrogen on this carbon. There would be 2 on this carbon. In our final product, there's now 2 here and 3 here. So we've added 1 hydrogen to each of those carbons. The reaction underneath it is the exact same thing, but using a more complex catalyst. I'm fine if you just say Wilkinson's catalyst. I'm never going to ask you to produce this formula on your own, but you may have to recognize that formula. So if you see this with rhodium and everything, it's rhodium, triphenyl phosphate, and then chloride. It's just making an alkene. The other important thing is that catalytic hydrogenation is a syn addition, just like hydroboration oxidation. So both hydrogen atoms are added to the same face of the molecule. So if you have a cyclic alkene, that can have some stereochemical implications. For a straight chain alkene, there's no stereochemical implication there. You can also reduce an alkyne. You can take it to an alkene, and then you can further reduce it to an alkane. So if you take an alkyne and you react it with hydrogen, and then there's this nickel boron complex, you end up with the cis isomer of the alkene. The more commonly used one is Lindlar's catalyst, which is hydrogen and then palladium on calcium carbonate. So it's calcium carbonate with palladium metal particles in the presence of quinoline, and you end up with the cis product. So Lindlar's catalyst, I would say, is the more common one. I'm gonna go ahead and say these reactions here, flashcard them. You cannot really flashcard the other addition reactions that we did. Like if you don't understand how they work, you cannot come up with the product just by flashcarding it. But these, I would flashcard. So have alkene plus hydrogen plus transition metal on one side, and on the other side, alkane, synthesis of alkane from an alkene. And then alkene, Wilkinson's catalyst, write the formula on there, and then on the back, alkane. Same thing here. There are two different ways to make an alkyne into a cis alkene. I would make two separate flashcards. And then we have a way to make a trans alkene, which uses lithium metal, ethylamine, negative 78 degrees. So this has to be done at a low temperature. Negative 78 is a temperature you'll see very often, and it sounds really random, but that's actually the temperature of an ice bath made from dry ice and acetone. So if you combine those together, you end up with a cooling bath that's negative 78 degrees. So it sounds really random, but it actually does come from somewhere. And then you finish that up with ammonium chloride. So I would flashcard this to cis, this gives you cis, this gives you trans. I think that's your best bet of getting these in your head. Okay, I clearly poorly animated this as well. So our next topic is carbenes. This is a minor topic. We're not going to use this a lot, but it is important because it's a carbon-carbon bond forming reaction. So this is an addition to an alkene, kind of. It's very different from the other ones. So, well, okay, I don't know why the nitrogen part was animated separately, but so there's this compound called diazomethane, and if it's exposed to heat and or light, it will decompose involving nitrogen gas and a compound called methylene. So notice the carbon here was negatively charged. When this bond breaks and nitrogen gas leaves, it takes 2 more electrons with it, which leaves us with a carbon that only has 2 hydrogens, a lone pair, and is somehow neutral. And it also gives us nitrogen gas. Now, this compound's methylene can be attacked by a double bond. Did I animate that? Nope. Okay. So you end up with kind of a cyclic attack, which creates a cyclopropane. There's also a compound or a class of compounds called carbenoids that are methylene metal complexes, and they do the exact same thing. So the outcome is the same. You create a cyclopropane. I will say that I typically put 2 questions about this on an exam, and it usually does not appear on the final exam. And I give you like a cyclohexane alkene with some other substituent on it, and then I give you CH2, and I expect you to draw a cyclopropane that is cis, a syn addition. The other type that we have is the dichlorocarbene. So if you take chloroform and react it with an alkoxide, you will end up creating this intermediate compound here, which the negative charge on the carbon is destabilizing. So the compound loses an equivalent of chloride, which stabilizes it into a carbene. Now, I say stabilize. A carbene is not stable. It's highly reactive. But this is more stable than the precursor. So it's not letting me erase that. The process to make this is really slow. And then when you introduce an alkene, it's going to react very quickly to create another type of cyclopropane, but it'll have chlorine substitutions on it. So these conditions here indicate that you are creating the dichlorocarbene. So this is potassium T-butoxide with chloroform. And this is the way this type of problem is usually written out. So you have your alkene, it says potassium T-butoxide and chloroform. You are expected to know that those conditions give you the dichlorocarbene. This is another one where flashcarding would not hurt the situation. Are there any questions about the carbene? You can tell by the amount of time that I'm spending on it that it's not one of the bigger topics in OCHEM. So usually, like, I would want all of you to learn everything and completely understand it. But if you get to a point where you're prioritizing things for the exam, if this is one of the things that trips you up, I would toss it in the trash for now and focus more on the other additions to alkenes, to elimination, substitution reactions. Those are really big deals. Those get used throughout all of OCHEM. The carbene is something that pops up very rarely. Okay, we also have some reactions that are oxidations of alkenes. So you can react an alkene with osmium tetroxide and pyridine. And notice this is a stepwise reaction again. We have step 1, step 2. And then you follow it with sodium hydrogen sulfite in water, and you end up with a vicinal diol or a glycol. If you can do the exact same thing by reacting an alkene with potassium permanganate in base and water at a cold temperature, you will get a vicinal diol. So this is an oxidation reaction of an alkene. This is another one where we don't spend too much time on the mechanism. I'm never going to test you over the mechanism. I'm going to show a little bit of it to you on the next slide, but I would flashcard these reactions. So here's a small amount of insight into the mechanism. The only reason I'm showing this to you is because if we do this with a cyclic alkene, you end up with a cis vicinal diol. The reason being that you form this cyclic osmate ester as your intermediate. And since this portion is cyclic, it's forced to be cis. And then when you follow up with the sodium hydrogen sulfite in the water, it maintains that cis stereochemistry. So anytime you have an intermediate that is cyclic, that cyclic structure has to be cis if it's attached to a cycloalkane. So this is the same for like the bridging bromonium ion. There's another way to do this. I've never tested over this, but I think it's really interesting. Osmium is not really something that you want to use a lot of. It can be toxic. You don't want it going into your chemical waste and then leaching into groundwater or anything like that. So there is a process created where you can use a catalytic amount of osmium tetroxide. in the presence of a co-oxidant to accomplish the exact same chemistry. So again, I've never tested over this particular reaction, but it's cool to know that like there is an option that's a little more earth friendly. So in this class, I'm fine with using the like, more theoretical concept, like we can use these reagents to cause this chemical change. But if you were to do something like this in a lab, this is how you would do it, because osmium is not something you want to have on hand and that you want to be putting into your chemical waste. Okay, our next topic is the oxidative cleavage of alkenes. And I believe this is our last chemical reaction topic in this chapter. We have oxidative cleavage, and then we have cleavage using ozone, which is reductive. So this can be summarized very easily in these 3 lines down here, which is why I color-coded very heavily. So if you take an alkene and react it with potassium permanganate, base, water, and heat. Heat is really, really important here. Remember, we've already seen these conditions before, and we created a vicinal diol. If you add heat, you're going to do an oxidative cleavage. So you're going to end up with a totally different product. So you end up basically dividing up the alkene into 2 carbon-containing pieces. That's why it's called a cleavage. It's because you're cleaving the bonds. If the carbon on the alkene is mono-substituted, meaning it has 1 carbon, it's going to make a carboxylic acid. If it's unsubstituted, note how there are no carbons attached to this carbon other than the other part of the alkene, which does not count. You will end up creating an equivalent of carbon dioxide from that carbon. If it's disubstituted, such as this one, meaning it has 2 carbon groups attached to it, you will end up making a ketone. So if you want to memorize something, that is what I would memorize, and then it's easy to apply it because it's not overly creative. There's no rearranging of carbocations or anything. You're just going to break it into 2 pieces and make a carboxylic acid out of this one, a carboxylic acid out of this one. Break this into 2 pieces, make a ketone out of this one, and a carbon dioxide out of this one. So this next slide is a practice problem, but it's kind of backwards. So I'm giving you the product, and I want you to figure out how this molecule looked before the oxidative cleavage. So I'm going to break you up into groups to do this. So go ahead and copy down the problem, and when you have it, go to your breakout room. I'm just going to give you about 2 minutes to work this one out. It's not too bad. Okay, so let's talk about this problem real fast. Anybody come up with an answer that they like? By answer that they like, I kind of mean, did anyone come up with an answer they're willing to draw on the screen right now?
No, because we only got as far as deciding that it was the dye substituted, and then we got stuck.
Okay. So I think the easiest way to handle this type of thing is you need to know that, oops, why? Okay, I was not touching the screen that time, so that was confusing. The two carbonyl carbons must have been attached to each other. That's the only way that this would work. So you have an alkene, and you guys nailed it on this one. This one must have come from a di-substituted carbonyl. So I'm going to draw those two R groups as part of this alkene. This one, since it's a carboxylic acid, must have come from a mono-substituted alkene. So this R group can be repeated. This hydroxyl group would have been a hydrogen. And that's it. And then when you do this type of problem, it wouldn't hurt to double check yourself. Like if I, broke it up here through oxidative cleavage, would this give me this ketone? And would this give me this carboxylic acid, So I think this problem seems a lot more challenging than it is. Does this make sense? How we got here?
I'm still
Kind of. Okay. So I mean, it's really just a puzzle. So you know that
I
this.
think I may have to revisit this a few times on my own before I get it.
Yeah, that might be best. We can look at. I have another type of problem that we can look at in a second. So there's also cleavage with ozone, which is what's called a reductive cleavage. So it's just called reductive because you don't end up with highly oxidized products. So it still uses the exact same type of cleavage of alkenes. And then there is a formula as well. Anything that is unsubstituted will get turned into formaldehyde. So here we have a CH2. It gets turned into an equivalent of formaldehyde. Anything that is mono-substituted gets turned into an aldehyde. So this portion here is mono-substituted. There's a hydrogen here. It gets turned into an aldehyde. So you can see the carbon and hydrogen framework is maintained. It's even maintained in this conversion to formaldehyde. So you can see the carbon with two hydrogens, the double bond, it's maintained. Carbon and hydrogen framework, carbon-hydrogen framework over here as well. Same thing here. You have a di-substituted carbon. You maintain the carbon framework. Mono-substituted, there's hydrogen here. You maintain that same framework. Really, all you're doing is trading out the alkene portion for an oxygen. Does that make sense? I'm trying to be nice by
Yeah.
not putting us
Oh,
through.
okay, I see. So basically, for at least for these ones, the O sort of represents where it's split.
Yeah, and it does in the other one as well. So here we had a di-substituted one that turns into a ketone. The carbon framework was maintained. Also, in either set of conditions, you get a ketone from a di-substituted one. The unsubstituted, you just have to know it gets turned into carbon dioxide. That's it. That's really simple, just straightforward. If you have a CH2 group, it turns into carbon dioxide. The mono-substituted, the carbon framework gets maintained, but you insert an oxygen here and in here. So instead of your other carbon and whatever on over here, you replace it with an oxygen. And then instead of just having a hydrogen here, we insert an oxygen. So the carbon framework.
Basically, you're just
Mhm.
so you're just putting oxygens basically, like where
Yep.
double bonds or a hydrogen is, you're just gonna
Yes.
replace it with
Right.
oxygen.
So you can also like draw out your carbon framework again, draw the double bond, but then instead of drawing the rest of the alkene, put an oxygen there. That is especially true for the reductive cleavage. Whoops. So for the reductive cleavage, just draw a line, redraw your carbon framework, draw your double bond, put an oxygen on it, and fill in your hydrogens. Here we had CH, CH2. Redraw my double bond, top it with an oxygen. So it's much more straightforward than it looks.
Yeah, that makes way more sense.
Yeah.
Since we did it so
Yeah.
fast at the time, I was confused, but this makes sense.
Yeah, this one
Well,
I'll
and I think
people up
before
for
we
about.
start- Oh, I was just, because we've done like, okay, this is what you're adding to it, and this is where you're getting the oxygen. It was just kind of like, boom, oxygen, and I don't know, it was just different somehow.
Yeah, that's okay. So, okay, let's do 2 practice problems. It's the exact same structure. We're just going to do one reductive and one oxidative. So go ahead and just do this by yourself. I'm going to give you like a minute because I think you can do it in a minute. Okay, let's talk this through. Even if you're not done, that's okay. Just keep working ahead if you feel like you were going to get it. So exact same process. We're going to break the alkene, redraw the carbon framework. 1, 2, 3, 4, 5, 6, 7. There are 7 carbons. So I'm just going to draw that out. 1, 2, 3, 4, 5, 6, 7. Now, carbon 2 and carbon 7 had the alkene on it. So I'm going to draw a double bond here. And I know that since this is the reductive conditions, I can just draw an oxygen onto there. Carbon 7 had a hydrogen sticking off of it. So I'm going to draw a hydrogen. Go and draw my double bond and put an oxygen on it. And that's all you have to do for this. Now, the nice thing is that since we've already done the hard work of, taking something cyclic and putting it linear, a di-substituted alkene makes a ketone with either set conditions. So I'm going to leave that. I know I'm still going to have an O, a carbonyl on this one, but a mono-substituted, oops, I'm circling on the wrong one now. A mono-substituted carbon in oxidative conditions does not make an aldehyde though. What does it make instead? So we're trying to figure out what goes here.
And alcohol?
Yeah, well, so it makes a carboxylic acid as the entire functional group, right? But we're putting a hydroxyl group here where the hydrogen was.
So what does that again? What makes that hydroxyl group?
It's because these are oxidative conditions. Potassium permanganate is an oxidant. We're not going to worry about the mechanism. It's not okay. My organic professor in undergrad used to kind of be hand wavy about things like this. He was a very smart man, and he just knew that inorganic chemistry was not going to fly for us. And so he'd be like, and then some black magic inorganic chemistry happens and you get this. And I'm perfectly fine with that explanation in this class. So through some black magic, this hydrogen gets turned into a hydroxyl group.
It's exactly how it feels.
Yeah. So these are just electrophilic additions, the same ones that we've been doing, but to alkynes instead. And I'm going to click ahead for you real fast. You'll see that the outcome is very much the same. So if you add a halogen across an alkyne, you're going to get a transalkene. If you add the halogen again, you end up with a ton of halogens on your carbons. So the carbon framework is not going to change at all. So if we take this molecule and we turn it and we react it with bromine, we're going to end up with the same carbon skeleton. So we have 7 carbons. Carbon 7 has a hydroxyl group coming off of it. And the alkene was between carbons 5 and 6. Oops. So we're going to end up with a transalkene with the bromines going in opposite directions. So if that forward process didn't work for you, you can also say, okay, this is carbons 5 and 6. I know that my bromines are going to be added in opposite directions. And then I need to put everything else that was coming off of these on here. So I need carbon 4, 3, 2, 1. Well, that was drawn very poorly. Wow. Carbon 4, 3, 2, 1. And I need carbon 7 and my hydroxyl group. And, oops, I accidentally clicked a button. So sorry. Whoa. Killing me. Okay. I think this is, yeah, this is where we were. So the addition of halogen acids to alkynes is the same process. You're going to end up with trans addition, but this one's a little more complex because it's a Markovnikov addition. So for the alkyne portion, it's not a huge deal unless this is a terminal alkyne, then you'd have to think about that. But once you react with the halogen acid again, if you are reacting again, you will end up with your hydrogens on the same carbon and your halogens on the same carbon. So this is a Markovnikov addition. So if we take our alkyne and we do our reaction, which carbon is the bromine going to end up on? Is it going to end up on, we'll call this carbon A or carbon B? Oh, shoot, it's 11:41. We'll pick up here next class period. We have about 4 slides left. So next class period, we will start off with our quiz and then we'll finish off chapter 8. We'll do some practice problems and then I'll let you guys go early for Friday because we are way ahead of schedule. It's time.
What's the main focus for the quiz?
That's a fun question because we did a lot this week, right? I'm just gonna go ahead and say there's not much of a focus, right? It's gonna be substitution and elimination and addition to alkenes. I would expect up to 10 questions. The majority of them will be, what is the outcome of this reaction type questions. So I would do some of the homework problems. I think most of the assignments are open. I'll go and open them right after class. Focus on the what is the outcome of this reaction type problems. So you're
Sweet,
given,
thank you.
yeah.
Gonna look kind of like our quiz today. Sorry, the quiz, the questions that we had.
Yeah, especially like the third question where you're given starting material, reagents, and you had to come up with the products. And I believe they will all be multiple choice. I don't think there's a structured drawing tool on Top Hat, but if there is, it's gonna be exciting.
But
Can you post any of the finished PowerPoints that
Yes,
you've
yes,
done?
I'll post them after class.
Yay, thank you.
All right.
thank
By
you.
after
Have a
class, I mean after lunch, by the way. I'm really hungry, so I'm gonna eat and then I'm gonna do a posting spree.
Cool, no worries, me too.
All right. All right, see you guys tomorrow.